Ma'am, good evening.
Hi, good evening, Anupam.
Ma'am, it is sorry to inform you that I got 30 marks in the last, what you say.
The last week assignment.
Yes, ma'am. So can we get the solutions, ma'am?
Uh, I think NPTEL itself would give you the solution. Is that not there?
No, ma'am.
What
Till
is
now,
the timeline? So, have they given you solution for week one
other
and two?
courses, I have enrolled for 5 courses. Other courses I am getting solution, but for this
Okay.
course I am not getting.
Hmm. Actually, like after every deadline, they should be providing you with the
Because then what
solution.
happen? We will go ahead and then we cannot compare where is the fault, So that
Right,
then
right. Yeah, they should give you the solution. One second. It's just that you know that your question is wrong or right. Is that what they provide you? Hello? If you're trying to speak, I think you are muted.
yes, sorry, ma'am. Actually,
Okay.
my point is now we are
Mm-hmm.
going ahead of the course. If we
Okay.
will compare our errors in the previous week now, then
Mm-hmm.
how do we learn the course? See, I'm sure that there must be small errors in. That's why I got less marks. But my
Mm-hmm.
question is either we should solve the complete assignment and then proceed in the next, or the detailed what you say solution should be provided.
Yeah, that's what was the pattern of the class, right? But in the last session, some of you said to like proceed with the current one. So the thing is, they should be providing you the detailed answers. So can you write to NPTEL and check with them if possible? Because they are
Okay,
providing for other courses, right? So this should be something they can check with the course instructor.
okay, ma'am.
And yeah, I think they should be able to help you. If not, then you can email me and then I can just upload the solutions in the drive.
So
Or maybe I
my
can do that in the next
my
session. If they don't do it by the next session,
my
I
request,
can try to do that. Yes, tell me.
my request is ma'am, my request is if you have a last week's okay solution, then you
Mm-hmm.
give us okay in that what the link what you give na in the drive so that we can
Right.
if you have
Yeah,
solved.
I actually won't have the exact solution, right? So I will have to also solve, and then because right now I see in the website they have just like highlighted the correct answer, not the like process how you got the answer. So I'll solve it and then I'll upload. This is what I'm saying. I can do that.
Yes, ma'am. Because what I want to say
Mm-hmm.
that if we proceed in the next and if we leave our previous doubts na, then in the
Right, right.
last it will be very difficult for us to okay clear because they don't give last time after 12th week, 13th week there is the exam.
Okay, okay. No, then I think continuous study will help.
Yes, yes.
Mm-hmm. No, I agree. See, you can mail NPTEL, and if they don't do it by next week, let me know, and then I'll try to solve it for you. Okay?
Okay, ma'am. Secondly, one more is I am using my tab. So there, okay,
Mm-hmm.
only numerical I can put numerical values. So now
Okay.
in any numerical, we have to give the
Mm-hmm.
units also, like meter per second. So
Is
that
it?
yes, yes, yes. No, I don't know. This time also one assignment was there. I have given the digits, but meter per
Okay.
second or that unit is also required to be put. Now, so when calculator are using, we cannot take what you say the units.
I don't think they need units for any of the question. Which question
Yes, yes,
specifically?
yes.
Could
They do.
you?
Now today, like this semester, sorry, this
Mm-hmm.
what you there is a problem in
Mm-hmm.
question number 8. Okay. And
Okay.
question number 7 is also having doubt. You can see, ma'am, you though you don't solve it, but this week, present week, this is the last week, present yes. So now,
So they say, right, number 8 is like find out the settling time in seconds. So you just have to put the number.
but that unit I is not required then. No?
Unit is not required. You just put the number. That's it.
Now,
Nothing
question number
else.
7, see, again there is doubt. What is the doubt? Now, if you see that frequency, so frequency is under root of k by m. That is the
Where?
formula.
Which question are you talking about?
Seventh question.
Seventh is this one, right?
Now,
Or
if you
some other
see the
question?
now if you see the formula for the frequency, which is under root k by m. Now,
Mm-hmm.
k and m both are reciprocal. Reciprocal. Now, if one thing will decrease, another thing will increase. Both of the answers they are showing decrease. K is
Okay, we'll
decreasing,
come
M
to
is
these questions. We'll come to these questions. We haven't yet started discussing, right? We'll come back to these.
decreasing. Is also having problem in this.
So any question? So wait, how many are there? We are three people, so I think we can start. Yeah, so good evening, everyone. Welcome to the session. So, this is week 4. We'll be dealing with these dynamical systems, modeling, stability, and controller design. So, I'll walk through from some of the topics in week 4 and then we'll come back to the assignment discussion. Before that, Anupam or anybody else, do you want me to clarify any of the questions in week 3 if possible? I'll do that for like 15 minutes and then we'll move on to the next week. Let me know.
If you can start from past question, if you can just give the answer, then at least 5 6 questions compare.
We can do the week 3 part in the end, I guess, because this is
Okay.
my first session, so I would like to start with something new.
All right, we can
Yeah,
do that.
thank you.
Okay. So coming back to this, so in this week, where is that? Yeah. So there, it is written that dynamical system modeling, stability, and controller design. So this is basically split into two parts in general. One is this continuous time modeling and control of dynamical system, and the other one is basically, I think, on the stability part. So before I move on to this, how many of you have already watched the lectures? So that I know if I have to go deep into some of the things or just skim through. Can you raise your hands?
I've watched the first 3 or 4 lectures, and then I started going through the slides before going to the lecture because I wanted to get an idea before I go to the lecture. So I've not watched all the lectures, but I did start watching them. 3 or 4 I've watched.
Okay, great. What about Anupam and Aditi? Have you watched the
Ma'am,
lectures?
I have watched all the lectures. I
Okay,
watched the slides.
okay, great. Aditi, anything from your end? Okay, so I think what we can do is since you have watched all the lectures and Shivansh has watched like the initial few lectures, the initial parts I'll skim through, but then in the later part I'll just highlight some of the details. Okay, so here, as is also pointed out in the lectures, we have this cyber physical system, and in this particular lecture, we were focusing on the controller and the control input computation, right? So over here, like there are these different components altogether, but then we have, yeah, I think not this, yeah, let's say cruise control system, okay? So over here, they say that it controls the speed by measuring the vehicle speed and you compare it to a desired or a reference speed and automatically adjust the throttle. So in general, whenever you want to go ahead with any control system or you want to do anything, you need to write their state space equations. Okay, so you need to identify the variables, and then somehow you need to identify the equations that are kind of governing that particular system. Okay, so in this case, this is a very, very simple example. Here, if the mass of the car is m, and then it is, so u is the force that is that is generated at the road or the tire surface, and then this bv is actually the drag force. Okay, so the equation goes like this. You have this m v dot, and v dot is actually your a, that is acceleration. So your um, mass into acceleration is actually force, and then you have this drag force. So summing up both of these is actually equal to the force that is generated at the road interface. Okay, and then we say that y is equal to v. So we are kind of having these equations properly. So here we say that v is equal to x dot, and what is x that they have chosen? Mm-mm-mm. Okay, x is in general displacement, and x dot is like velocity. And then you have acceleration, which is v dot, which is actually dv by dt, right? And this is actually dx by dt. So this is kind of shown in this way in the control systems part. So acceleration is your x double dot. This also you can write as d square x by dt square. Okay, so this is how things go on.
What is y there?
Where?
The
Over
last
here.
equation. Yeah.
Yeah, they are just saying probably that you're assigning v as some variable y. So over
Okay.
here, if you write, it will be like m y dot plus by is equal to u. On
Okay. Okay.
u
Okay.
also, I
Yeah.
think they might say like u can be x or something like that. Okay.
Okay. Yeah.
All right. Now in this dynamical system, we have two specific things. One is this state vector and the other is a function. So state vector is like these variables that you need to describe your system. Okay. So over here, when we were talking about the state vector, you will have your like this v and a. These are different things, but then eventually you just have your x, and if you want to represent it in terms of y, that you will do. So we'll look through some examples later. And then there is a function that is actually transforming your current state to some future state depending on some, like control parameters or like the input that you get. Okay, so here, let's say this is a state vector xt, and you have different of them, and t is like x is like parameterized by t. So over here, for any state determined system, you know the state variables at an initial time. This is important. You know the system inputs for time t greater than 0. So you need to know what is the input that is going in your system. You know the initial state, and those two will be enough for you to predict the future state or output. Okay, so that is the thing. Then we have the state variables. They are kind of, they characterize the system state at any time t, and the number of state variables n, it actually should be equal to the number of independent energy storage elements. Okay, so in general, just consider this, that the state variables that you pick out from your system, they all should be independent of each other, and in no form, like let's say something else is the derivative of something else, right? Like let's say x2t is like derivative of this. That shouldn't happen. Okay, so now, yeah, let's say we have this kind of a function, and there are multiple functions also that can be there, and then you have these different state variables, and then x1 dot is represented by this, and that probably could be represented by function of all of these entities. Okay, so there are different kinds of dynamical system: linear, non-linear, then autonomous, non-autonomous, conservative, non-conservative, discrete, continuous, and 1D multidimensional. Okay, so by linear system, we mean that any equation that you put out, like the state equations, they should satisfy these two basic properties. One is additivity and then homogeneity. So if your equations are satisfying these two, it is a linear system. If not, it classifies it as a non-linear system. So if an equation is like this, fx plus y is equal to fx plus fy, and sorry, fx is equal to 3x. This is an example. So this is kind of a linear equation. But then over here, if you have like a parabolic, so that is not a linear equation, or even if you have something like xy, that's not a linear equation. Okay. The other classification is this autonomous and then non-autonomous. So here there was this one part that if there is a shift in your input and if it reflects in your output also, it means that your system is autonomous, otherwise it is not. So if you take this example right over here, if this is the example yt is equal to 10 of xt, now there is a delay that is introduced in the system, which is x of t plus delta. So your yt is actually going to be 10 of x, I mean 10 times of t plus delta, right? Now you see this other example. Where is it? Yeah, yt is equal to t of xt. Okay, so if you introduce the delta again, so it will be actually t plus delta into this x of t plus delta, right? So this is actually not reflecting the actual changes in the output in a similar way as the x was changed. So this becomes non-autonomous and this becomes autonomous. And in the case of autonomous, if your independent variable is time, it is called as time invariant system. Okay. All right. The other one is very generic. It is conservative and non-conservative. So in the case of conservative, your energy remains constant. And over here, there is some kind of dissipation that is happening. Now you have discrete and continuous should be there somewhere. Okay. We'll come to it whenever it is there. So this is described by a difference equation or a set of difference equations. All right. So let's say over here we say that x of 0 is equal to x and x of k plus 1 is equal to function of something. Okay, so over here they represent this k for the time. Okay, so at every time step, this is what is happening to the value of x. So you can consider those as the different time steps or so. So this is like the initial value, and then at the next time step, you get this value, and then after that, you get this kind of a generic thing. Again, one dimensional and multidimensional. So over here, if you represent some kind of an equation where your a and b are just constants, it is called as a 1D equation. And then if you have multiple multidimensional, it means that your a is actually a matrix and your b is a vector. Okay, so these are fine. I guess we can skip this. Yeah, feedback system will be there. Like if you have output of one going to the other and input of one going to the other, something like that, you have this feedback loop. And that, yeah, so this is one important thing. So over here, whenever we want to do some kind of a control, so we have this sensing, computation, and actuation. So the major goal of these control system is these three. The system should be stable and the system should have a good performance. By good performance, we mean that it should respond rapidly to any changes. Okay. And the system should be robust, which means that if there is any kind of changes in your external environment or any kind of perturbation, then your system should be tolerant to those things. Okay. Yeah, so then another kind of this classification, this is where your feedback comes into picture, and then we have our transfer function. So if there is some kind of response that is given and then something is actuating and then you have the process, so this is fine. This is a open loop. And if you have some kind of a feedback going back to your like this controller, that is called as a feedback. Okay, and that is actually a closed loop cycle. So over here you have control over this part, and that will actually make some tuning, and that goes over here, which goes back to your controller to make sure that whatever values you have used at the set point, that will eventually work out. Okay. So these are fine, I guess. Yeah, I think this is a good diagram. So for this closed loop, what we have is, let's say you have set some set point or reference input, which is like, let's say you want to maintain 50 degrees Celsius somewhere. Okay. And then there is a controller which wants to, like tries to maintain your whatever air condition or whatever heater is there, and that is set to this 50 degrees Celsius. And then you have the actuator that is actually doing the actual work. And then let's say some kind of a noise is there. So this disturbance is actually acting as a noise. Then you have your process. So whatever is your actual output, that actually goes back as a feedback, saying that let's say over here you said 50 but we are getting only 40 degrees. So for the error that is produced, which is just 10 degrees Celsius, the controller will do changes according to that. So if initially this was 0 degrees Celsius and this error is going to be 50, so the controller has to make changes faster, right, to reach the set point. So these kind of things happen at the controller level, and this error actually plays a major role, and to get the error we need to get the feedback. Yeah, I'm actually trying to get some example of the state space. But yeah, okay, we can start. So about the state space representation, you have this system, you have a controller, and whatever output you have from the system, that is actually your states. Okay, and some of the states you can send back to the controller, which goes back to the system. Okay, and then we have some kind of a noise. So over here, we have this state as the smallest number of variables again, such that the knowledge of these variables together with the knowledge of the input that completely determine the behavior of your system. Okay, so you can have it as a state vector. So state vector is actually this n-dimensional vector whose components are n state variables that describe the system completely. Those were that x, y, and so on, right? And then you have the state space. So this is actually the n-dimensional space whose coordinate axis consists of the x1 axis, x2 axis, and all of that. So I think these will be cleared when we go through some examples. Let's see. Yeah, let's look at this for now. So there are these two different kinds of um, state space models. One is continuous time, one is discrete time, right? So let's say over here we have this continuous time. So this we have also seen earlier. So we just represent it like this. Okay. So your A of T is actually your matrix, right? So this was your matrix because this is multidimensional over here. We are considering this as a multidimensional, and your B is actually a vector. Either it can be a vector or a matrix, depends on how is your UT. But UT in general is like a single dimensional. I mean, it's a vector, so you need to have a vector over here. Okay, so these two are actually your independent variables. And if you have some kind of a discrete time state space, you have similar kind of equations. But then if you see, this T has actually changed to K. And this is what we also saw earlier. Yes, Anupam, you have a question?
Ma'am, can you give us example wherein, okay, once second order equation we can represent in this form?
Yes,
A.
yes. Actually, there is example. I'm just trying to search for that.
Also,
Like,
what would be an example for discrete time space system? Because I don't think it is like I don't get a practical example because time will always be continuous. So
yeah, correct, correct. Um,
No, but
Actually,
in
there
the
are not
time,
many,
like,
like questions or something also based on that, like on the discrete time.
ma'am,
But if you actually
my
want to hmm
ma'am, can I say, ma'am? See,
Yes,
time is
yes.
always a constant, but if you use constant, okay, equations, lot of memory is consumed. So we make a controller in discrete time, sampling time, so that the memory and processing is fast. So that is the reason wherein all continuous system is converted into discrete system.
Yeah, but he is asking for an example. Like, where do we practically use it?
And any examples like temperature is not 50
Yeah.
to 60. It will become 50, 51, 52, 53 like that. So we can have step of five, na, or step of two
I
like
think
that.
it's more about the representation, Shivans. It's
Yeah, I
not
get
like,
it.
yeah.
Yeah.
Yes, let me see if there is an example, but for timing, I'll continue this. And very likely the examples are right there. I think a spring damper system is there, maybe, but we'll check.
We had questions in the assignment as well for spring damper system, like 3 or 4 of them. So yeah.
Yeah, I think the first 5 questions are based on that.
Yeah, so we'll get to that anyways.
Yeah, right. Okay. So about this time response analysis, let's see. So again, over here also we have some questions in the assignment. So this actually means that you want to kind of analyze the behavior of your system with respect to the time. Okay, so you mm, 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 mm. Yeah, so you have inputs that are function of time, you have outputs that are also function of time, and then you want to see the behavior of your system. So there are these two different kinds of responses. One is a transient and the steady state. So let's say if this is like your full timeline axis, and then this is some kind of your output. Okay, so whenever something starts from zero, so let's say when you want to start your vehicle and you say that you want to go to 50 km per hour or so. So initially, while the starting phase, it has to go from zero to some value, right? And then after that, you are kind of like, okay, we are at 50, so it will remain between, let's say, 40 to 50, or maybe if it's like proper cruise control, you will have lesser variations. So in that case, the initial phase where you're actually starting up, that's called as a transient state. And when you have actually reached your steady state, which is like the set point, that is your steady state. So by steady state, we mean that this part should actually, like, as time tends to infinity, this should be a constant and that should be equal to this value. I don't know why they say over zero over here. The time required to achieve transient response. Okay, this should actually be T, first of all. This is a correction that is even made in the lecture by the professor. Okay, so I think this is like the transient response becomes zero as time tends to infinity. So that is fine. And then steady state response is like it is the behavior of the system as t approaches infinity after the transients have died out. So again, a very short example is this Ct is equal to 1 plus 10 e to the power minus 2t. So if your time tends to infinity, this part becomes 0. So your final part just remains as 1. So your um, like transient term is this, that becomes 0 as t approaches infinity. So your steady state value is going to be 1. All right. So those are the things. And then I guess these are like standard test signals. And I think after this, they talk about the Laplace transforms. So there are a few of these signals that are important and you should just know them in general. And whenever you practice more, you would just kind of remember the equations also. Okay, so this is very simple. It's an impulse signal. Then we have this step that whenever t is greater than equal to 0, it becomes some specific value. And if it is less than 0, it is 0. Okay, and then we have the ramp signal. Then we have the parabolic. And there are certain relations between these standard test signal, which means that if you integrate impulse, it becomes step. If you differentiate that, it becomes impulse. That is straightforward. But if you integrate step, it becomes ramp again, and the ramp, when you integrate, it becomes parabolic. Okay, so these are the things. And from Laplace transform of these test signals, you can just know that these are the Laplace transforms. Okay, because for impulse it is a constant, and for step it is by s, and then by s square and by s cube. Like this is the usual Laplace transformation. Okay, so before we start this transfer function, any doubts?
No, I guess none from my side.
Okay.
Yeah.
So what I'll do is I'll cover transfer function, then I'll skip the rest of the parts because I want to go back to the questions and assignment questions, and then take one theory at a time depending on what is required. Okay?
Yep. Okay.
Because, yeah. So let's see. So over here again, you have some kind of a, what is this? RS? Okay, input function which is coming in. Then you have your error. Then GS is actually your open loop gain. This is the gain. And then CS is your output. HS is your feedback loop gain. Okay. So this is how your transfer, I mean, this is how your, in general, a closed loop feedback cycle works. And what is your transfer function actually? Before that, you need to check that it is a time invariant system. Okay. And then you calculate this transfer function as the ratio of Laplace transform of the output to the Laplace transform of the input. Okay, so that is thing. So over here you will say CS, Laplace of CS, Laplace of RS. This is actually going to be your transfer function. I don't know how that is represented. Yeah. Okay. And then we have these notions of poles and zeros because depending on this, your system stability is defined. Okay. So the poles of a transfer functions, these are actually the value of the Laplace transform variable s that causes the transfer function to become infinite. And these are actually the roots of the denominator of your transfer function. So whenever you are asked to calculate the poles of a transfer function, uh, they would actually ask you to calculate the poles of a system, not in general transfer function. So you have to calculate the transfer function first, check the denominator, and then get the roots of the denominator. Okay. And then about the zeros, this is actually that these are the values of those variables which is causing your transfer function to become 0. All right. So obviously you have to make the numerator 0. So these are the two things. Okay. If you want to calculate the zeros, you have to make the numerator 0 because your transfer function should become 0 for those values of s. And if you want to calculate the poles, you have to make the denominator 0 and calculate the roots because those are the values of s, because of which your denominator becomes 0 and because of which your transfer function becomes infinite. So is this part clear?
Yes.
Okay. Mhm. Okay, so this is fine. Yeah. So there are these some transient unit step response specifics. So there are a few equations that are derived, obviously, but these are the simplified versions of those derivations, which we can in general use for most of the cases. So there is this time constant tau, and this is defined as the time required for your equation to decay 37% of its initial value. And then you get that as 1 by a. You have a rise time, which means that the time that is required by your waveform to go from 0 0.1 to 0 0.9 of its final value, which is like 10% to 90%. You get that as 2.2 of a. And then you have a settling time, which means that the time required by the response to reach and stay within 2% of its final value. So you get that as 4 by a. Okay, so I guess with these equations, let's start with some of the examples. Oh, I'm sorry, I didn't say about what is A over here. So this is actually your initial slope, okay, which is 1 by time constant, and that's how you get this 1 by A over here. Okay, so let's see. So the first question is about a buck converter, which is a step down DC to DC converter that consists mainly of inductor and two switches. So this is in general, they are explaining how this DC to DC converter works. And then we have that it switches the connection of the inductor to source voltage to accumulate energy in the inductor. So there should actually be a, like, it is like this. There is a switch over here. Okay. And whenever you want to charge your inductor, it connects to the voltage, like a power source. And whenever it wants to discharge the inductor's energy, it just, the switch opens up. Okay. So you are not no more connected to the power source. So that is the basic idea over here. So it says that clearly the control input to the system is your source voltage, okay, which is your V in. And the system's output is the voltage across the load, which is this. Okay, so this is your VC and this is your V in. All right. So now they also have given these equations according to the Kirchhoff's law during its off mode. Okay, the only change during the on mode would be that this won't be zero. And during the on mode, the equation from KVL will actually be L di by dt plus Vc is equal to U. That will be some kind of a value. Okay. And so now the question says that you calculate the transition matrices for the off mode. Okay. So what you have to do is, before that, I'll actually share a paper that actually has done this full derivation. I won't be doing the full derivation right now, but then this paper will help you. Let me see. Hmm. So I've shared a paper in the chat window. Are you able to access that?
Yes.
Okay. So on page, it actually starts section 2.a. Over there is this buck converter state space model. And they have spoken about both the cases. Like if you look at equation 3 and 4, they are for the on case, and the other one is like for the off case. So that is the thing over here. Yeah. So what we can do is we
Paper is
can
not
have.
accessible. Paper is not accessible.
Okay, I'll just upload the PDF. Then let me download and upload it. Are you able to access now? You are still not able to access. Check now. I think it should be accessible now. Yeah, but with the current version, I have enabled for everybody in this chat. So it should be available.
It still says that it is only accessible by the accounts that are associated with it.
Okay. You were you able to open in the browser when you said that you are having access to it?
So the thing is, I had the IEEE, so I have an account that allows me to access those, but it won't be available for everyone else. So,
Right. So will you be able to download and upload it over here in the chat window
wait,
for others to access? I'm not sure if my institute is not allowing that.
I'll have to check. Wait,
Sure, sure.
yeah.
Okay.
Uh, is there no drive link for this? If you have the PDF available on your laptop, you can just share it
All
around.
right. Yeah, I
Yeah.
can do that. So we have our drive link over there itself. I'll be uploading now. Yes, I've just uploaded in the drive. So let me know if you're able to access, and that's a good idea. I can put the screenshot as well. Just let me put that right away. But you should go through the paper to understand what's going on in the question. Okay, so in this question, we have this, like again, as usual, we have to set the different um, variables. So we have chosen x1 as the current and x2 as the voltage, and they are independent of each other, right? So we need to come up with the equations that actually show these both of these equations properly. Okay, so if you have this, like you need to take out the derivative of this, okay, both of them, and then you have to rearrange them such that it is in this format. x1 x2 is equal to, you will have this is your matrix A, okay, you will have x1 and x2, and plus it is going to be, this is your B. um, so as I said, during its on mode it is like this, right? DIL by dt plus V of C is equal to U. So you can just check like how it is going to be. So basically this can be U. Okay. So will you be able to solve this question based on the materials shared and the initialization of the variables?
What is can you explain the role that C is playing here? Like I get the role of A and B. What is C here? C is from the KCL equation.
What did you say? C is from the?
KCL equation, the when which was given initially in the question itself.
Mm, I don't think so,
Yeah,
because
that's what I was
C
thinking
is
as
more
well.
like the capacitance, right?
Yeah, so what is C
Mhm.
in the final answer, the options?
It may be like this, just a constant. So this C is different from that C, that is for
Yeah,
sure.
yeah, yeah.
So I think it should be this, like plus C.
Okay. But like, guess we should be able to conclude the answer only from A itself because the options are all different, I guess. No, okay. One of them is. Okay, yeah.
Yeah, you can check. I mean,
Yeah, I'll check. Yeah, okay.
yeah. Okay, so let's move on to question 2. Yeah, this is where this spring mass system with damper is there. So let's see. Again, over here, the very first thing for every equation you have to do is to check what are the exact variables. And this question is asking you what are the state variables for your system. So you need to identify like properly that which ones are dependent and which ones are independent. So over here, the question is this spring mass system with a damper. Okay, so this is your damper, and Ft is the force that is exerted on the mass m that faces a displacement of yt due to the force. So this is a force that is being applied, and this is the displacement because of the force F. Now K and B are the spring constant and the damping coefficient. So here the equation is also given. So you have to identify what are the state variables for this system, right? So you have to say fx, let's say you identify that y of t is equal to something like x1. Then what are the rest? So you have this dy by dt is equal to x1 dot, right? And
Yes.
you can say that this b of dy by dt is, where is it, x1 dot plus k of x1 plus m. You still have to actually check because mm, that's actually your x double dot. um but this and this is actually having the same unit, so you can think carefully and then choose your answers. Okay.
Same unit as in, aren't all of those having the same unit?
So actually it like if you solve these equations, right, it should come like this, something like this, and then you have the other one on the other side.
Okay. Is there any specific reason for writing it like this? I mean, we have to calculate for FT
um,
only. So like
yeah,
putting
you do that,
MX.
but actually in the next questions also, when we try to solve these, it becomes like that. So that's how
Okay.
these equations go, like, because eventually you have to simplify. Over here also you would see that in the paper they have simplified it a lot, to make
Yeah.
it, like x1, x2. They substitute so much, and then they kind of want to get something which is totally independent of there. So if you look at any of these A matrix, they don't have anything which is having like your VC or IL or anything, right? So
Yeah.
it should be independent of your x1 and x2. So that's how it becomes also. So you need to just check this properly and frame the equation for this equation of motion. Okay, let's see what is the second question. This says, what is the state transition matrix? Again, we have to calculate this A. And input to state transition matrix for the spring mass damper, again from the above, considering the exerted force as input to the system. So your force is your input. All right. So over here, they have already told you that this is your U. Okay. So again, all the like more reason to shift it to the other side and keep this alone. So maybe your equation should actually become like, what is this? d2 yt by dt square. So you should simplify it like this. 1 by m of bx1 dot minus k of x1 plus f of t, which is basically your u, that is your input to the system. So now in this question, if that is the case, let's see what happens. Yeah, so your equation earlier was f of t is equal to b of dy by dt. I'm just not putting like this, but you can put that when you are solving it. This is k of y plus m of double derivative of y. All right. So let's say if you have your x1 is equal to y of t and you have your x2 is equal to y dy of dt. So your x2 is equal to x1 dot, right? And then over here, what do you say? You have this u, or like you can just put f for now. F minus b of x2 minus k of x1 divided by m, that is equal to your x2 dot, right? So again, that way you need to identify that x1 dot and x2 dot. You get this. This is your going to be a. You have your x1 and x2 over here. So you simplify this and put this a very properly. And then you will have this as b. And over here you will have your f. Okay. So one correct way is to do like this, x1 dot, x2 dot. The other way is to do it like x2 dot and x1 dot. So you can get a different answer for this particular thing, right? So there can be two answers over here. One will be in this format and one will be in this format.
I have a little doubt with the previous one actually.
Yes.
When we say, for example, in the second option, displacement, acceleration, and speed of the mass,
Mm-hmm.
aren't speed and acceleration just derivatives of displacement? So why are we choosing them as state variables? You said they shouldn't depend on each other, right?
Yes, they actually shouldn't depend on each other. That is true.
But like for all of the options,
Hmm.
something is depending on the other thing. Like
Yeah. So over here, the way we are putting this is like, hmm. So it's more like choosing the variables and then mm.
because like the
It is
equation that
slightly
you
dependent in the
yeah
physical world. You are right.
yeah
Hmm.
because like the equation that you came down to, it had both all three, displacement, speed, and acceleration. But is it actually depending on
Correct.
all three?
Yeah, so I think over here, like what we can say is like as the state variables, you have your x1 and x2. That is definitely there.
The
But
displacement
yeah,
part,
over
right?
there in
Yeah,
the here they had put right that they need to be independent.
independent of each other. Yeah.
Hmm. Yeah, this is actually the tricky part of these state spaces because it becomes the way you actually model your system, right? The way your equations also become. That's why I told over there that you may have multiple answers.
Yeah.
Where was this? Let me just check if they have something specific written. I don't know. Mm-mm. Is it later somewhere?
I'll have to check. Wait.
No, no, it's over here. Hmm. They say that number of state variables n is equal to the number of independent energy storage elements in the system.
So in this, there are two energy system. One damper, one is spring, and mass is also an energy. So that
Oh, right, right. Okay, you're right. Yeah. Hmm.
energy can be stored in only spring. That's
Yeah.
it.
Right, right. Yeah, so this is the spring and it is your damper. So your variables is supposed to be equal to 2. Okay. So should I move ahead?
How do we get to those two? Like, how did you choose which two?
So you actually start with one first and then you move on to the like usually we start with like whatever is the variable given, you say that is like x1
Yeah. So,
and
for
then you
example,
move
in
ahead
this case,
with
it will
that.
be the displacement.
One is
And
displacement.
yeah, and then we move on to like we move on till which point of time? Like we can differentiate. For the force, we'll need the acceleration as well, but that depends on the speed, velocity.
Mm-hmm.
So
Mm,
we just take the first two because we need to, or is there another approach?
but I'm just thinking because your acceleration is actually like the output, right? I'm just thinking if
Yeah.
that is still one of your variables.
Okay. Yeah.
Um,
Actually, fair enough.
yeah.
Because that's okay. Yeah, makes sense. Okay.
Mhm. Okay, again, a follow-up question over here. So this question says that we have that spring mass damper system, and then this is the representation of that in the Laplace domain, in the S domain actually. So we have to identify the blocks that are labeled with this 1, 2, and 3. Okay, so let's first see what was our equation and let's transform that to Laplace. Plus k of yt plus m of ut square. Okay, so if we have done this Laplace conversion, we will have our output, which is over here. Then your equation becomes b of s plus k plus m of s square. This is your fs. Okay, so what was our, you have to represent actually the output in terms of the input, and that's how you are going to get these. So so your f of s minus this y of s into bs plus y of s into k is equal to m of s square, right, into ys. So your s square of y of s is equal to 1 by m f of s minus y of f of bs plus y of s of k. Yeah, so So now what do we have to do? Did we have Laplace? Did we go through the Laplace transformation section yet? I think we stopped here, right? At poles and zeros. Okay, it's not provided, I guess.
Yeah, it wasn't in this PPT.
Hmm. So we basically have to identify like this is your one part that is going to your error calculation and this is the other one. So this is like your fs and 1 by m, right? So this is actually your fs into 1 by m that's actually going inside this, right? I mean going inside this block. So what are the other two? The other two are definitely these. Um, but the thing is they are going in different from different points and both of them are not ys. So even if you calculate one of them as this ys, okay, there is one s over here, right? Sorry, I just didn't see that. Okay, so I think this one should work now. So there are these three inputs that are going to your, I mean, to your control system, right? So 1 by m is definitely for all of these. So whatever goes here has to go through this 1 by m. So 1 by m is definitely there. You have your fs, and then the rest two are actually coming back from your output. Okay, so you can put these things that way. Is this kind of clear as to how you can approach with this hint? Let me know if I should move to the next question.
Yeah, one more minute. Yeah.
Okay.
What should be the thing that is there after the first block, the first dot on the first line?
So you need to see
Yeah.
that what should be over here such that it comes to this equation.
Okay.
Because your ys, so let me just put it very specifically, your ys should be equal to 1 by s square of m f of s minus ys of b of s plus ys of k. Is that clear?
Yes. 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 Okay.
I think if you do the, because eventually you have to get ys, right?
Yeah.
So you can just do it that way.
Yeah, okay.
Okay. So the next is again a derivative of the same question. It says what is the natural frequency omega and the damping ratio of the spring mass damper system given in the question. So express the denominator of transfer function in this part. Okay, so hint is already given to us. S square plus 2 and what was our transfer function in the S domain? We had this, right? Ys already and fs. So your output is ys, your input is fs. I'll still write it over there. So ys is equal to, sorry, ys is multiplied with this ms square plus bs plus k is equal to fs. This is what we got from the last question. So now what is your transfer function? That is ys by fs, because that's the ratio of output by ratio by input, both in the Laplace domain. So this is actually 1 by ms square plus bs plus k. Okay, so now you have to express this part in this form. Okay, so this is what we have to do. So now let's say we have this ms square plus bs plus k. Let's do it over there itself. Okay. So first of all, you have to get s square. All right. So let's make this 1 by m. This becomes s square plus b by m s plus k by m. Right. And then what can we do? We have to get the something over here. And I mean, we are eventually going to this format of getting this omega n, and we are trying to separate out this part and this part. So you already have this s over here. So we are trying to get this wn such that you extract some wn from here, and then whatever is left behind, that is your tau. Okay, so this is your s square plus b by m of s plus k by m, the root of whole square, right? What does this become? It becomes 1 by k. So you took out this part, and your numerator, sorry, your denominator became 2 times b by root 2 km, okay, into root k by m into s plus root k by m the whole square, right? This actually should be wn square, right? If I'm not wrong. I think there is some typo in the question, because how else are you supposed to take out that part over here? Okay, so I think if you do that, this should work. Is this okay?
Yes.
All right. So I'll move, but please feel free to stop me whenever required. So the next question says, in the system given in this question, stable, question 2, stable in open loop for the following values. Oh, is the system stable for these values? So what you have to do is you actually need to check the poles and zeros. And let's go back and then check over here. So we actually need to check this part. Yeah, I mean, this is the exact slide that I was looking for. So when you calculate your poles of the system, and how do you calculate the poles? You want your system to go to infinity, which means your denominator has to be equal to 0, right? So you first calculate the poles of the system, And then you do an analysis on top of that. So if your poles lie on this imaginary axis, it means that your system is marginally stable. So this is the case where it's marginally stable, which means that your values are fluctuating between two values. And then if it is stable, which means that your poles are actually having negative real parts. So if that is negative, which means that they will die down after some time and they will become stable. Okay, but if they have a positive real part, which means that it is going to grow like on, and then it will become unstable at a point. All right, so what you have to do over here in this equation is you have to get your denominator over here. You need to get this value, okay, which is your s square plus b by m into s plus under root by k, yeah, this part. um but this is not the one, right? You have to get your m also. M was a part of it. Actually, just get the initial equation that you had, which was s square plus, what was it, ms square
Plus
plus
BS plus
bs
K.
plus k,
Yeah.
right? So you convert this to 0. Okay, substitute these values which are over here. All right, solve it and then analyze what values you are getting. Okay, and you have to
So
check the
yeah.
sign of the real part, because the stability depends on this, right? This is what it is. Maybe take a screenshot and then paste it there for you all to. Okay, so you can do your analysis on top of this. All right, let's go to the next question. This says match the following for the open loop system for the dynamics, again given in question 2. So yeah, I guess you can still do the analysis based on this value itself. So if your b is 0, right, then what is going to happen? So if you have this ms square plus bs plus k is equal to 0, right? In case your b becomes 0, what happens? Your s square is equal to minus k by m. So eventually your s is imaginary, I guess, right? So then you can check that if it is imaginary, which means it doesn't have a real part, right? Then what is the case that if you have your poles on
It
this? Yeah.
keeps
So you
oscillating,
can keep that.
like
Yeah,
you
I
said.
mean, you have to make a choice. I won't tell you the answer.
Oh yeah, yeah, okay.
But yeah. So, and then you can just analyze that given this equation again, if you decrease k, what is going to happen? So basically, get the equation of s in plus minus a plus, I mean, this format. Okay. And then you try and analyze for all these cases that what is going to happen.
Okay.
All right.
Ma'am, in this, I have one question that if you see
Yes.
K and equation that is reciprocal, So now, okay, if one is K is suppose decreasing, then
Mm-hmm.
oscillation is increasing.
Hmm.
Uh, and suppose if M is also decreasing, then
Hmm.
oscillation is increasing. So if you see the answer in the right side,
Right.
uh, the
Yeah, makes sense. One has to be increasing.
this is my what you say error, no? The
Okay,
error in the
okay. Now I understand what you were saying. Yeah, yeah. I mean, that's a fair question. So, what you can do is for now, let's see what is the equation that we get. We usually get minus b plus minus b square minus 4mk by 2m, right? So, I think mhm, for the one case, it's fine. Let's say if you want to increase k. Hmm. Hmm. I think based on these options given, um, I would suggest you to consider this part. Otherwise, you won't have like options matching each other. Okay, so consider this. But even if whatever answer you put, I think NPTEL should send a clarification later that what was this part? I mean, what was the correct form of this question? Because it doesn't make sense to put both of them. But still, let's see. I don't want to just give you some false thing. So even if your k is decreasing, all right. No, it's fine. I think this question is okay. Both of them can decrease. So you have to like, so analyze in this format that what is going to happen, okay? And then you match with these questions. The other question
First,
is correct.
you see B is equal to 0. Okay. Now, if you
Okay.
B is then the same equation what you have told initially, na, S is
Mm-hmm.
plus minus Km, that will come.
Right.
Now, if B is equal to 0 and then S is equal to plus minus K by M, so one
Mm-hmm.
is and M are reciprocal. And so if one is decreasing, then S is the basically the frequency. Okay, so one will increase then.
No. So the thing is, this is one part. Like when your b is equal to 0 is one part, right? So consider equations in three different formats. In the first one, only keep b is equal to 0, which is this part for you. Analyze this one and then choose an option. Okay. In the second one, pick this equation, try to decrease the value of k, and then analyze what is going to happen. In the third case, again pick this same equation, increase the value of m, and then see what is going to happen. So s is equal to 0, k is
Okay,
decreased, m is decreased. These all are three independent questions. Okay.
I have to take B is equal to 0 for all the cases. Okay, then.
No, 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 no. B is equal to 0 is only for one question. Okay. Should I move to the next question now?
Yes, yes.
All right. Okay. So the next question says find out the settling time in seconds to settle within 2 seconds of the steady response. Again, over here, there was some timing analysis that we checked. Where is that slide? This one, right? So we need to find the settling time for the given open loop system in question 2. You have to consider these. So you need to actually calculate this 4 by A. And what is your A actually? We need to calculate that. Let's see how that is done. Yeah, your A is actually this part, right? 1 second. This equation, I mean, over here, the denominator that we had, this is what is your A, if I'm not wrong. right? So you can then calculate 4 by A for this question. I think this should be fine because you would have already calculated this omega in that question and even the tau, and then you can calculate this. This should be okay. But make sure that these values that they have given are the same for the two questions, okay? Here m is 2, b is 1, and k is 1. Mm-mm. Yeah, so you can, substitute the values over here and then you can calculate, because see, for every question these values are changing, so just be careful when you substitute these values and then you get the answer.
Okay.
Yeah. All right, so the second last question is about this HA. For the open loop spring mass chamber, again the same question. When we are using this Ackermann's method to place the system's pole at this, use the state transition matrix corresponding to the... Okay, again a very different value of m, b, and k. So we have to refer to Ackermann's method. This was towards the end. Okay, so with these methods, so basically we have to design your feedback gains based on how you want your output to be. Okay, so we kind of know where the poles are going to be. Okay, and then we design our gains based on that. So you can go through these slides just to understand what is happening. So there are two methods to it. One is direct substitution, the other one is Ackermann's formula. So in the case of Ackermann's formula, what happens is you have to check the controllability of the system, and then you have to choose the desired closed loop poles. The closed loop poles are already given to you as minus 0.8 and minus 0.8. Okay, and then based on this Ackermann's formula that we have to calculate this. So since you are given only two of the poles, right? So we will just have two of these. So basically we are going to have h of a is equal to a minus lambda 1 I, a minus lambda 2 of I. Okay, and what is your lambda? Both are equal to 0.8. All right, so based on that
A, ma'am,
you should, sorry,
can you help for A, ma'am?
A is your state transition matrix that we already calculated. Here it's written, no? Input to state transition matrix for the same question, question number 2. So we would be having from here, right? You would be getting your A from here, correct? And that is what we are going to substitute over there. Okay, so this is your A, and then you have your input to state transition matrix. That is given as 1 by m and 0. That's already given over here. Okay, so using that, you can calculate this, like, I mean, you can get the answer from there. You just have to solve the equation. So will you be able to do this? Yes, no,
Yes,
doubtful.
I guess doubtful, but yeah, okay, I'll try.
Okay. All right. So moving to the next one. This is more about a MATLAB function. Let's see what it says. Find out using which MATLAB function among the followings you can calculate the time constant of the same question for this value. Okay, so we have to use system is equal to TF, which is probably the transfer function, coefficient of numerator, coefficient of denominator function to build the transfer function, okay, of the second order system in order to use it as an input. Then check for the description of the following functions with help command and run them using the transfer function. What is the question? Find out using which MATLAB function among the following you can calculate time constant. Hmm. Yeah, so I think they have already given these instructions. If you do this, like you have to provide the coefficient of the numerator of the transfer function and the denominator. So you just put those and then it should give you, but this is not required, right? If you just want to get the help of the function name. Yeah. Maybe you have to just initialize a system first and then you can help using these function names. Just check out which one of that actually like is used to calculate your time constant. I think this also should be fairly easy. This is more of an exercise, I think, that
Yeah.
they want you to learn about these functions. Okay, so any questions? Because we don't have any questions, and I think if you have gone through other details in the slide, that's good. But yeah, we have covered almost everything that's required for the assignment. Any doubts or any questions that you would want me to discuss now? Okay, if not, I think we can close the session for today. We'll meet next week, 6 p.m. again. If any of you have any doubts, please feel free to stay back. Otherwise, we can close it. Thank you.
Thank you.